Howdy folks. So in my last couple videos you would have seen me talking about a dangerous Chinese mains lead. And one of the things that I discovered about that lead was that the two primary wires were reversed, live and neutral were reversed. And I know there's going to be at least one of you that's thinking in the back of your mind, why does that matter? And that's actually quite a good question. There are a lot of devices which have plugs that you can put in both ways. So why does it matter? And so this is going to be kind of my explanation towards this. It's also a new style of video. I'm going to try doing sort of a live screencast drawing thing, and let me know how you like this. So in order to understand why certain devices should only be plugged in one way, we need to sort of backtrack a little bit and talk about some fundamentals of electricity. In particular, I want to talk about voltage. Voltage, it has a couple definitions depending on whether you talk to a physicist or an engineer, and some of them can be far more scientific than others. But basically, voltage is electrical potential. So think of it this way. If I have a rock and it's on the ground and I pick that rock up and I lift that over my head, then what I'm doing is I'm giving that rock gravitational potential energy. It has the potential that if I let go, it will fall down onto my head. And with electricity, voltage is sort of a similar thing in that what you're doing is you're giving electrons the potential to create an electric current if you provide them a path by which to do so. This is where Ohm's law sort of comes in. The most famous and probably one of the most important equations, V equals IR, voltage equals current times resistance. What this basically means is that if you provide a non-zero resistance, i.e. you provide a path for current to flow, if you have a non-zero voltage, if you have some potential, you will get a current out of it. Now, if you talk to a physicist, they're going to tell you that every object in the universe has a non-zero voltage. And when they say this, they're basically talking about the charge on an object. And from a physics definition, in order to have zero charge, zero voltage, you have to basically be infinitely far away from another object that is charged. So obviously in the real universe, that's not something that happens. But what engineers usually care about is not voltage as an absolute value, but basically relative voltage, so a change in voltage between 2 points. Now, physicists will refer to this as delta V, or the change in voltage, but engineers just refer to this as just straight V. And this is basically, whenever you see V as in voltage, that's pretty much what they're talking about. It's a relativistic measurement. And you may ask, well, what is it relative to? And the answer is it's completely arbitrary. And this is kind of the crux of this video. So if I have a simple circuit, let's say, for example, it's a DC circuit. And just because, let's make it the thing you probably would have seen in your high school class. We have a battery, and we have, let's be super old, and let's draw an incandescent light bulb. I wonder when kids will stop knowing what those are. Anyway, so we have our little light bulb. Okay, cool. The simplest possible circuit that you can probably draw. Now, the question is, this battery, let's say, I don't know, it's a 9-volt battery. Okay. So what we're saying is, we're saying that the potential difference between this terminal of the battery and this terminal of the battery is 9 volts. But the question then becomes, well, if I were to just take a some sort of measurement probe device and I was to connect it to the circuit here, what's the voltage? And the answer is you can't do that. You need to have two connection points. You need to have another part of that probe, and you need to connect that somewhere else on the circuit. And the voltage measurement that you get is the difference between the two. So you can't say, what is the voltage at this node? You need to know what is the voltage at this node relative to another node. And it's because there is no 0 point in a circuit. If there is a point in a circuit that's considered 0 volts, it's completely arbitrary. So what I basically mean by that is, I could say this node of the circuit, this is 0 volts. 0 volts, just to be more clear. This is 0 volts, and I'm only saying it's 0 volts. There is nothing that makes it any different from anywhere else in the circuit. That's just what I've arbitrarily assigned. And in that case, going through the battery, that would make a point up here, plus 9 volts relative to this, because the battery is 9 volts. There's absolutely nothing wrong with me going, okay, this point up here is 0 volts, in which case this node down here is minus or negative 9 volts. That is completely okay. There's nothing wrong with doing that. That's fully valid, and in fact, you'll see this done in many, many places. So where we assign 0 is completely arbitrary in a circuit. Now, in a DC circuit, generally we will use either the lowest voltage or basically the most common voltage. Whoever's designing the circuit will pick basically the easiest node, or one of the most common nodes, and call that 0, and everything will be taken relative to that. Obviously, if you had a more complex circuit than this that actually had more than just 2 nodes, of course, things would start to sort of make more sense. So you may ask what this has to do with mains and which way around the plug goes in. And one of the reasons why you may ask that is because mains is AC, and that means it's alternating current, so it doesn't really have a positive and a negative, because they keep reversing, they keep changing. So why does this matter? So let's say that in our simple circuit here, that we were to make this node here what we're calling 0 volts. And the way that you display this on a schematic is you use the ground symbol to indicate that that is the 0 volt reference point on the circuit. But just for the completeness, I'll put in an actual 0 volt marker there. And let's say that we want to know what the voltage at this node, the other node, is in this circuit. So if we were to just graph this quickly, and in this scenario, we've got 0 here. This is time on the x-axis, and this is voltage on the y-axis, and that's 0. And let's say, I don't know, this is 10. In this example circuit, the voltage would be constant with time because it's DC, and it would be at 9 volts, of course. And I think this makes sense. I don't think that there's any doubt about this. It's quite simple to see this. However, let's say that we had instead an AC power supply. So let's say instead of this 9 volt battery here, let's say we had an alternating current source. So I'm just going to draw in a symbol for it because, of course, generating AC is quite a bit more complicated than generating DC with a battery. So I'm just going to put in the symbol for that. So let's keep everything the same. Let's keep this 0 volt reference, and this one is what we're looking at. So let's do what we just did as before, and graph the voltage at the top node relative to the bottom node. Exact same graph as before. 0 volts are on this axis, arbitrary time is on this axis. And that node, that signal, is going to look something like this. Let's assume that it's a sinusoid. And okay, so that's my pretty terrible sinusoid, but let's say it looks like this. So what you can see, of course, is that the voltage on that node is going up and down, and it's going positive and negative with relation to this bottom node here that we've called 0 volts, which is this line right here. So in some cases it is above, it's positive, in some cases it's below, it's negative. Now, we haven't really defined what this 9-volt measurement is, because this 9-volt measurement could mean a couple things. It could mean that this here is 9 volts. It could also mean, this is called the peak voltage. It could also mean that this is 9 volts, which would be called the peak-to-peak voltage. It could also mean the RMS voltage, root mean square voltage. And I haven't really said what this is. Let's define it. Let's say it's the peak-to-peak voltage. So it's the voltage from the top to the bottom. So in this setup, we've called this bottom node the ground, or the 0 volts, and this node at the top is what we're looking at. Now, let's suppose that we had reversed these, and we were using this top node as ground, and the bottom node was the one that we were looking at the voltage. It would be, basically, it would be the opposite. It would be the negative of that. Okay, that was a bit horrible, but you get the idea. It would be the negative of that, because you're basically taking everything relative to the other point. So now that I've been going on about this for quite a while now, you may ask, how does this really tie into mains electricity? If you look at a North American power outlet, if you look at the receptacle in the wall, you're going to have basically a large or a long prong, and then you're going to have a shorter prong, and then you're going to have your ground prong. And this is the way it is in North America. Of course, there's so many different standards around the world, but this is the one that I'm going to look at just for this video. Now, these prongs actually do have 3 different names. Of course, the one on the bottom is ground. The small one is what's called live, or sometimes it's called hot. And the large one is called neutral. So what exactly these are all connected to is sort of the crux of the matter. So ground, the term ground, you'll notice that I used the term ground over here. What ground refers to is the actual earth, the dirt that you stand on. Basically, this ground pin is effectively connected into a metal rod, which is staked into the ground somewhere in your house or your apartment building or wherever you happen to live. So you have effectively a wire that comes from this, and it goes underground. And what this does is this provides sort of a reference point for electrical circuits. Like I said, nothing is actually at 0 volts. Everything is arbitrarily assigned 0 volts on a per circuit basis. However, the actual ground, the earth that you stand on, is sort of referred to as 0 volts, simply because it makes sense to reference everything to the largest object in the world. That is, it is the world. So that's just sort of, it's used for a lot of safety aspects. You can shunt power to ground in the event of a fault. It's also used for a lot of other things. that I won't go into this video. The actual power in a main circuit comes from live and neutral. Now, live and neutral, of course, the difference between these two has to be your mains voltage. So if you live in North America, you are probably familiar with the notion that your outlets provide 120 volts AC. Now, this is the RMS measurement. This is root mean square. And what RMS basically does is it gives you a value that allows you to approximate power with relation to a DC circuit. That's not terribly important for what we're talking about today, but the actual voltage between these two pins is actually much greater than 120 volts. This number, like I said, is exclusively used for power measurement calculations. In North America, if you remember the quick diagram that I drew of the AC waveform, the distance from the top of the peak to the center line, this is the peak voltage. In North America, the peak voltage is 170 volts, and the peak-to-peak voltage, which is from the most positive peak to the most negative peak, which is this total measurement, is V peak to peak. That is 340 volts in North America. And so you can imagine that the UK is quite a bit higher than that. So just as with our simple example circuit here, we have to have a reference point for our AC waveform. And ground is not the reference point for our circuit, of course, because you can have two-pronged plugs that don't have a ground on them and they still work. The reference is actually neutral, and that's sort of why it's called neutral. If you were to graph basically live versus neutral, it would look exactly like the diagram that I drew earlier. Neutral is effectively neutral is 0, and live alternates positive and negative with relation to the neutral pin. So as with my example circuit earlier, there's nothing that stops me from making this top node 0 and taking everything with relation to that. There is nothing that stops me from taking the live connector, making that the reference point at 0, and then taking the neutral relative to that. There's nothing that stops me from doing that. And it doesn't affect the circuit at all. So this is sort of why people would normally think, well, why does it matter whether live and neutral are reversed? And the reason comes down to one very simple thing. Neutral, somewhere in your house, most likely down by your circuit breaker panel, and in some cases it actually may be done in a transformer or something on a telephone pole on your street. The neutral is actually connected to the ground. And this is the reason why a reversed mains cable can be so very dangerous. Now, a reverse mains cable will not prevent anything from working properly. It will not stop. It won't interfere with the AC in any way. If you were to take a multimeter and you were to probe between the ground pin and the neutral, you'd actually find that there probably isn't very much of a voltage difference between those at all. Because of course this connection is going to be made quite far away from the outlet in your bedroom, for example. There may be a couple of volts or so induced through wiring and stuff, but the voltage on that pin will be very, very close to ground. And you, by standing on the ground, are pretty much ground referenced. So if you were to please do not do this. But if you were to stick a screwdriver into the neutral pin of an outlet that is wired correctly, you probably won't die. And it's because there isn't a very high voltage on that pin. The actual high voltage with reference to ground is on the live. So even though the live pin is referenced to neutral, since neutral is tied to ground, there is also a voltage difference between the live and the ground. And in fact, again, do not do this, it is theoretically possible to power an appliance between live and ground. Very, very dangerous. Do not do that. But it is technically possible. And in fact, there are some quite interesting places in sort of remote areas where, let's say you have like a cottage or something and you're extremely far away from all civilization. The power company, this is an interesting aside. Let's say that you live, you have a cottage, it's on a remote little island or something. No, not an island, it's just in the middle of nowhere. Okay, so you have a little house and it's in the middle of nowhere. Now, due to quite a bunch of laws, the utility companies, in particular the companies who supply electricity, are not legally allowed to charge you more than anyone else in that area for power. Now, let's say that you don't have electric service and they want to, they have to run some wiring to your shack in the middle of nowhere to provide you with electricity. Now, what they could do is they could make a bunch of poles, and on each of those poles, they would then string two wires. They would string a neutral to the house, and then they would string a live to the house. This is sort of not how they do it, but you get the idea, right? So the current would flow one way, and then it would return the other way, and then the next half of the cycle, that would reverse. And the current would flow this way, and then flow that way, because of course it's alternating. Now they could do this, and let's say that this cottage is, for the sake of argument, it's 20 kilometers away or something like that. Then they'd have to run 40 kilometers of wiring, of course, both directions. Copper is expensive. So what they could do, and what they actually do in some circumstances, is they will simply not bother to install the neutral, and they will only provide a live wire, because it now costs them half as much in copper. And you may say, well, how does the circuit work? Well, what they do is they use the ground as the return path. So there's a stake which goes into the ground on this end, and then over near civilization, of course, there's another stake that goes into the ground. And the circuit is pretty much this. They pass current through the live, and then it returns through the earth. And then the next half of the cycle, that reverses. And they do this. Now, the losses are ridiculously high because, of course, copper is a very good conductor of electricity. Earth is not. But it can be cheaper for them to just lose the electricity through the ground than to install two sets of wires. It's just sort of how cost-benefit analyses turn out. But it is possible to complete a circuit with the earth. It's just not recommended. So anyway, so we've established that you are standing on the ground. You are at effectively the same potential as the ground pin. And as a result, you should be very close to the potential of the neutral pin. Thus, if you touched something that was connected to neutral, you're probably not going to get shocked. But of course, the live, you definitely are. Now, the reason why some devices have plugs that are polarized, i.e. they have one leg that is physically larger than the other, such that you can only install it in one direction. The sole reason for doing this is for safety, basically. And I'll give you an example of an appliance that would do this. So let's say that you're in your kitchen. Of course, in your kitchen, you're going to have a toaster. And toasters, they are mains-powered appliances. And let's see if I can draw a toaster. Cool. Works perfectly fine. So with your toaster, you're going to have some sort of a plug, and it's going to have a long lead and a short lead. And I guarantee you that pretty much every toaster that has been made within the last couple decades is going to have a polarized plug on it. It's not going to be a non-polarized, i.e. they're both going to be the same length. It's going to go in one way and one way only. And the reason for that is actually quite simple. Inside the toaster, of course, there is a heating element, right, which snakes down the side of your bread, and of course that gets very, very hot and makes nice, yummy breakfast. So this, of course, has to get connected across the mains somehow. So I'll draw this as 2 wires. Actually, to make this easier, we will draw this using the blue for neutral and the red for live, just because. And of course, there's a switch in the front of your toaster. So I'm just going to draw that switch as sort of the circuit diagram type switch, because this is a very simple diagram. So the question is, how do you hook up the mains coming in to this heating element and switch? Now, it's AC, which means even if it was DC, it wouldn't matter. Electrically speaking, from a it will work standpoint, you can hook it up either way. It doesn't matter. However, from a safety standpoint, there is a way that you should hook this up and a way you shouldn't. Let's say that I decide to hook it up arbitrarily this way. Now, think about this for a second. Everything, of course, will work. You close the switch, the heating element gets hot as current passes through it, heats your toast. Then the timer goes off, the switch breaks, toast pops up, or maybe doesn't pop up. Maybe you're like me and you have a shitty toaster and it doesn't actually pop the toast up properly. So you've now got to get your toast out. So you've probably been told never to use a knife to scoop or try and pry the toast out of your toaster, but I know people do it anyway. So let's say that you were to do that and your knife was to accidentally slip. And in doing so, your knife came into contact. It actually touched the heating element inside the toaster, which is something that I have seen happen. It does happen. So if that were to happen, of course, the knife is metal, and it's going to conduct that heating element, which is just basically it's a bare wire, to you. And if you trace back, you'll note that that wire is connected to the live. So just like I sort of said that the live is taken with reference to the neutral, which is taken with reference to ground. You are standing on the ground, you are reference to ground. So the live is going to pass through the heating element, through the knife, through you, into ground. And that is not going to be a very pleasant experience whatsoever. So that's not good. That's definitely not good. But what if we reverse these? So let's say that we connected the neutral to the heating element there and the live to the switch like that. Now let's replay the same scenario. You're an idiot. You stick your knife in your toaster and you touch the heating element. Well, now the heating element is connected to the neutral. And the neutral, somewhere in your house, the neutral is connected to the ground you're standing on, which means they're roughly at the same potential. So even though you're completing the circuit, there's not very much potential between the neutral and the ground, i.e. you. So there's not going to be, you're probably not going to get a shock from this. And it's because the hot is protected by the switch. Now, of course, if the toaster's on and you stick something in it, it doesn't matter how it's wired, you're still going to get a shock. But in this situation, it makes the device safer when it's off, when it's switched off. And there are a lot of devices that are like this. For example, your hairdryer. Your hairdryer has all those heating element coils in it. Well, if you notice, your hairdryer will have a polarized plug on it. And it's so that if you accidentally stick something up the front of your hairdryer, it doesn't electrocute you. And you can actually verify this. If you take a multimeter and you unplug your toaster, you take a multimeter and you connect the heating element to the neutral, you should either get continuity or it should be open. There are some toasters, like my toaster, which actually has two switches. It actually puts a switch in both sides. And the reason for this is just purely safety. So it actually connects both sides, so you're completely isolated from the mains. But only much newer toasters will do this. So this is sort of why you don't want to have a cord that is wired backwards or an outlet that is wired backwards. And if you want to check an outlet in your house to see if it's wired backwards, it's very easy. All you need to do is get a multimeter and put it on AC volts and measure between the neutral and the ground, and you should get something that is very close to zero. And if you measure between the ground and the live, you should get something that is approximately, whatever your mains voltage is in your country. If you get the opposite, then your outlet is wired backwards, and you should get an electrician or do it yourself and fix that, because that can potentially be quite dangerous. So hopefully this has provided a bit of insight into why that reversed cable was actually so dangerous. And hopefully this has given you a little bit of insight into how grounding schemes work. Thanks for watching.